Hey guys, so I'm gonna now go over the isomorphisms and 2-3 tree Microteach. So as always, we're gonna start with the invariant. So what makes a 2-3 tree a 2-3 tree? So this time we're gonna split it into the invariants for a node and then invariant for a tree. So here we go. We have two different types of nodes. We have a 2 node and a 3 node. A 2 node is a node that has exactly one key and two non-null children. So illustrated, this means they have one key. This has one specific value in it, and it has two non-null children. Looks kind of like a BST. Okay, and then a 3 node is that the node has exactly two keys. Has exactly two keys. So each of these here and here have different keys, and then three non-null children. So one goes to the left, one goes down, one goes to the right. So that's the invariant for a node. And then a tree is that a 2-3 tree can only contain two nodes and three nodes. And then a 2-3 tree is a search tree. And essentially a search tree just means it's possible to read the order of such a tree. It can be tricky though at times. All right. So next we're going to talk about what is an isomorphism. Like, why do we keep on saying that word? And so an isomorphism is just a fancy way to say that there's a one-to-one correspondence or some sort of mapping that we can do. And in this case, the mapping is between a 2-3 tree and an LLRB tree. So we can always convert from a 2-3 tree to an LLRB or vice versa. And we have a note here that a 2-3 tree is not guaranteed to be a BST, right? Because it can have this 3 node, which has 3 children and 2 keys per node, which is not allowed in a binary search tree. But you can turn it into a binary search tree by converting it into a left-leaning red-black tree. All right, so next I'm going to go over the steps for how do we convert from a 2-3 tree to an LLRB tree. All right, so one thing to just note when we think of this is that think of a 2-3 tree represented with a BST invariant. And what that means is that we know that in a BST, everything to the right must be greater than, and everything to the left of a node must be less than. And also, there can only be at most 2 children to a specific node. All right, so now let's go to the steps. So the first step, and we'll go over this in more detail in the next few slides, is that we split the node with 2 keys. So we call this a 3 node into 2 different nodes, a left and a right. So we see this one has 2 keys, we want to split this, and we want to split this. And then we're going to attach the left 2 children, so the left 2 children, with the left parent, and the right one, so this one, with the right parent. And then we raise the right side up and we glue the parent nodes together. All right, so we're going to move on to a more specific example, which we actually saw on the previous slide. So the first thing to convert this into an LLRB tree is we take the 3 nodes, and we have one here, and we have one here, and we're going to split them and connect them with a red edge. I forgot to mention this earlier. Whenever we split 3 nodes, we have to split them and connect them with a red edge. So that's very important, actually. And so here we do that. One thing to note, why do we make the 7 go up here and the 8 go down here? It's very simple, and you'd have to think about it in terms of the LLRB tree invariance, where we know that a red edge always has to be left-leaning. So if we were to raise the 1 up to the top, it would be 1, and then because it's a BST, 7 has to go to the right, and we have to connect it with the red edge because that's the rule, but this is now a right-leaning red edge. So that is not allowed. I hope that makes sense, and you can apply the same rule here where it has to come down because it's a left-leaning edge. Okay, and so next we move the child subtrees for the 3 node. So if you recall into the steps that we mentioned earlier, the left 2 children belong to the left parent, and the right child belongs to the right parent. So that's the basic step we do every time, and that's essentially what we've illustrated here. And then we move these up. Nothing is actually changed in our tree, by the way, between these 2 steps. It just looks nicer in this case. And this is our finished result. This is the isomorphism to the LLRB tree. So for all intents and purposes, the data is stored the exact same data is stored in the previous 2-3 tree here as is here. So I hope that example made sense. Next, I'm going to go over tree height. So one key thing, I'll let you guys go over this slide at the beginning, few items, just to see if you agree with these observations and if you can think of some examples for this. But essentially, if we want to figure out the tree height between a 2-3 tree to an LLRB tree, the main thing you can do is you can convert it using this process that we talked about in this example. The other way, which is sort of like a equation that we can use much faster, is this one, where the height of an LLRB tree is equal to the height of a 2-3 tree plus the number of 3 nodes. So I think we have an example here. I think we actually talk about the reasons why we do this, but I won't go over that right now. I just want to go over the example. So here's our 2-3 tree, and here is our LLRB tree. So what is the height of this 2-3 tree? Well, one thing to note is that we count by edges. We count height by edges. So we have 1 and we have 2. So the height of the 2-3 tree is going to be 2. So we solved this. And then we have to look at the max number of 3 nodes from a root to leaf path. So this is the root and these are the various leaves. The max number of 3 nodes I'm seeing is we have 1 on this path, 0 on this path, 1, 1, and 1. So the max number of 3 nodes is going to be 1. And so 2 plus 1 is 3. And then we can confirm by switching into an LLRB tree that, yes, that's in fact true. The height of the LLRB tree is going to be 1, 2, 3. So I hope that makes sense. This will be useful if you want to do asymptotic analysis, like we say earlier on the slide, just because it helps you figure out how many levels you traverse through. Though you don't have to worry about that in this class. We likely won't be asking you something like that. All right, so this is the final part of the assessment or final part of the microteach that I will be going over from class today. However, I will also be uploading a video with an example on how to rotate an LLRB tree and how to do insertions. All right, thank you guys for watching.